Hey everybody, how you doing today? Coming to you from bright and sunny Philly. So we've got chapter 14 to talk about today, our recursion topic, and then I'll have a second video for about the final project that we can get started on now. Again, we are skipping that last project in interest of it's just so much stuff going on. So you've had a couple other individual projects here. I'm a little behind on the grading on those. I'll get those to you as soon as I can. So that'll be it for the individual projects, and then we'll start that final project, and we'll have up and through the last week to do it. Again, these other weeks aren't going to be quite as heavy, so even with recursion, won't be quite as heavy today. I don't know if you look at ahead of the slides, there's only 31 slides. Not that that's a good gauge of exactly how much time to spend, but there's not as much content to go through there, so that should be nice. We can get some time to get started. And it is, I guess I'll talk about it more in the final project video, but you're welcome to do this one in pairs. You just need to let me know if you're going to work in a pair or not. If we were in person, I actually would make people be in groups for this final project, but I know just group work is going to be hard given all things considered. So we'll just do, if you want individual, if you want to pair up, great. Also find people in the Discord or however you want to do it. I can set up channels for you, or you guys seem pretty good at finding ways of communicating, so should be good there. And then we've got nothing going on next week for Thanksgiving break. Again, if you want to start on the project, great. If not, you'll have the 3 other weeks to do it on out, and we can go from there. So I started up a new project already, and I've got a new source file here. So the main idea with our recursion is we've done functions, right, where we say, okay, here's my function that will do this thing, and we can call the function that does that thing. What makes recursion different is that the function calls itself, which might sound a little silly here, but there's some really easy ones here. So if we just make a void function, I'm sorry, let's put all of our usual stuff in here. So we'll include, if you can spell it right, IOStream, and we'll use our namespace, standard, and we'll have an int main function just for our entry point. Eventually we'll return our 0, and great. So I'm going to have my function up here. So if we have a void function like, I think the book likes this countdown one, that's fun, int number. Again, I'm not a fan of n. I mean, just sure, number, whatever. So with a recursive function, in order to be able to solve something recursively, you have to identify 2 things. And not every problem is solvable via recursion, right? It's a good fit for certain problems. And as you study more about data structures and algorithms, it's a really good fit for some things, but not everything. So if you can identify 2 things, it might be possible to use recursion to solve a problem. So the other approach, if it's not recursive, it's just functionally, versus a recursive solution. So you can have a functional solution or a recursive solution. So not every functional problem can be solved with recursion, but every recursive problem can be solved functionally, but sometimes it's just not as easy. And we'll look at some of those cool examples like the Towers of Hanoi later on in the text that show us why recursion is just such an easy way to think about this sort of problem here. That's the difference between the two. So you have to be able to identify 2 things. So the first thing you need to identify is when the problem is done. Right, so when do I know countdown is done? So I can say if number equals 0, right, then I'm done. That's the easiest thing. I'm going to see out blast off. I don't know if you guys saw the NASA rocket launch here. Was that space shuttle mission with the SpaceX rocket? Sending out 4 more astronauts. That's pretty exciting. I'm a big nerd, and I think that stuff is pretty cool. So we watched that here at the hotel. That was pretty fun. So that's our easiest case. So if number 0, we're done. There's no more work to do. We've solved it. We call this the base case with recursion. So the base case is if we reach 0, we're done, we blast off. Now we have the complex case. And we can say else, if we're not at 0, well, how can we make this problem simpler? How can we approach the base case? And that's the second thing. So first you need to be able to identify the base case when we're done. And second, you need to be able to identify how we can take a complex problem and break it down, make it approach the base case. So in our case, we're going to see out, the number, and I don't know, I think they did like ... for fun, ... and then we're going to call ourselves. We're going to call countdown, again, given number -1. We're going to approach the base case in that the number is getting smaller and smaller and smaller and smaller here. So if it's a complex problem, if it's bigger than the base case, we're not at the base case yet. How do we approach the base case? How do we make it simpler? So in our case, we just subtract 1. So now I can say, we'll call countdown, say from 10, and it should be, that's not 0, okay, 10, And we call it with 9. Well, it's not 0, so 9, call it with 8. It's not 0, so print 8. And count down, count down, count down. So what you're going to see is this really cool call stack thing. So if I put it in debug mode, every time a recursive function calls itself, we're adding a call to the stack. So we've seen this before, especially if we get a stack trace and we get errors. This call stack over here on the right. Let me make sure the video is not hiding. Oh, I can't actually see that very well. Well, hopefully you can see the call stack. I think I'm just losing the little corner here. So we were at main line 22, now we're at countdown line 7. So every call in the stack, remember C++ is tracking so it knows where to go back to when we're done, when we've called functions. So we're going to step, 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 and then I want to step into, to make sure I go into the call function. And now I was at countdown line 14, now I'm at countdown line 6. And what happens is every one of these calls, you need to track the variables inside the function. So number, because we're passing by value, so we're going to have another instance of number in memory here. So it can be a little expensive when in terms of memory. Oh, I did not want to step into that one. I want to step into this one here. Right, so this one was at when countdown was 10, number was 10. This one was countdown, number was 9. This countdown number is now 8, and we're just going to keep going and going and going and going. Let me put the breakpoint here. I think we want to continue, step in, continue, and step in. And we'll see we get a bunch of these, right? Number keeps going and going and going. Going 5, 4, 3, 2, 1. And I just have them all in the stack. So there is this thing called a stack overflow. You might be familiar with that term, where we put too many things on the stack and we run out of memory. It's possible to do. So we do need to be a little bit careful and cautious when we're using recursion, that we don't go, they call it going too deep, right, into the call stack, where we just have so many things on the stack because we've called it thousands and thousands and thousands of times. So you just need to be a little bit cautious there, but we should be okay in our case here. And what we get then is 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, blast off! Boom. And that's done. So that's a simple recursive example here. So other ones you might be familiar with, and I know all of you guys are math fans, right? Because you're taking programming classes, and everyone who likes to program must love math. It's an official rule. We're going to have a function that returns an integer called Fibonacci. Probably spelled like that. Fibonacci. You know what? I'm not actually sure how to spell it. I'm just going to Google it or Bing it here. Okay, I spelled it wrong. There we go. Oh, 1b. Okay, 1b. So Fibonacci, given an int. This is the, it's not the number of the Fibonacci sequence. It's like I don't know, I guess it's the nth number. So like the first term, the second term, the third term, the fourth term, the nth term. There we go. I like that. We'll give you nice and specific. And if you remember the Fibonacci sequence here, we'll just thank you, Wikipedia. Any Fibonacci number is the sum of the previous Fibonacci number plus the sum of the previous Fibonacci number. And it turns out you get this really cool golden ratio thing going on here with Fibonacci. It's such a really cool math thing. So you start with 1. I guess they say it starts with 0, but I've never understood that. I always assume it starts at 1. And we'll say, well, 1 plus the next value, 1 is the previous 2. So the sum of the previous 2. So 0 plus 1 is 1. Great. The next value is the sum of the previous 2. So at 2, our next value is 1 plus 1. And then 3, the value is 1 plus 2. And then 2 plus 3, 3 plus 5, 5 plus 8, 8 plus 13, on and on and on and on and on and on. It's really cool. The Fibonacci sequence is awesome. So we kind of build out this cool little spiral here as we're going. So, but the definition is super easy, right? So our simplest term then, we can say our base case is if the nth term is, I don't know, less than or equal to 2, right? The first two terms, the first term and the second term, are both a 1. Return 1. Else, and really the else here is redundant because we hit return. We don't really need an else. We're going to return Fibonacci of nth term minus 1 plus Fibonacci of nth term minus 2. That's it. That is the mathematical definition of Fibonacci. This is a recursive solution to Fibonacci. Now, you might be thinking to yourself, well, we didn't need recursion here to do Fibonacci because we can do the math and like count up. Yes, we could. We're just looking at an example. And this is why sometimes a recursive solution is like simple, super easy, and very straightforward. You're like, oh, okay, I know what this is. Because, I mean, Fibonacci is recursive by definition. That's just, mathematically, it is recursive, so it fits very well. But what happens here now if we do like Fibonacci 10, you know, let's do a loop for fun. So we're going to say for int nth equals 1, nth is less than, I don't know, let's just do the first 10, nth plus plus. We'll print Fibonacci of n. Okay, and then an end line, right? We're going out and we'll watch this run. We should get all the numbers, right? 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. Perfect. Works very well, right? We got the definition. Now what's going to happen here, though, let's take a look here. We want to put a breakpoint in here, and let's just start at 10, just so we can show you this example of 10. And I want to show you this call stack. And we're going to see why this is actually a very bad solution, because it's very expensive in terms of what's happening. So we're just going to step a bunch of times, continue a bunch of times here. Let's see. So I don't know if you're looking at the call stack here. Let's see. We're looking at value. There we go. So keep getting value, value, value. So I've got a bunch of calls in the call stack here. Let's see. 10th isn't too bad. Okay, let me stop that. Let's go up a little higher. So 10th isn't too bad. So let's do 20 and 20. Okay. So let's do this here. Okay, so we're at 20. So our nth term is 20. And we're going to see what happens as we keep hitting continue in the call stack. So it's going to go from 20 all the way down here, right? So we get 18 calls or so there on the call stack, right? Because we know if we're less than or equal to 2. That was for the first recursive call here for this one. So we said, okay, at 20, I need to give you 19. 19 said, okay, well, I need to give you 18. 18 said, well, I need to give you 16 or 17. And 16, let me draw this out here for you. And we can see what's going to happen here. Start a blank document. Right, so let's draw. Come on, pen, work for me here. Okay. Right, so at 20, it is the sum of 19 plus 18. 19 is the sum of 18 plus 17. 18 is the sum of 17 plus 16. 17 is the sum of 16 plus 15. Well, this 18 now is the sum of 17 plus 16. This is 16 plus 15, right? This 16 is 15 plus 14, and this one is 16 plus 15. This 16 is 15 plus 14, and this 15 is 14 plus 15. And you can just imagine this thing like spidering out like this crazy, every one of these calls needs to do so many other ones. And the problem is what happens is every one of them needs to get down to 1. So what we're going to get once we solve whatever the 20th Fibonacci number is, 6,765, is it has literally added 1, the number 1, 6,765 times. And sure, the computer's relatively fast at doing that. So if we do this and just hit run here, it'll think for just a second and do it here. But now let's continue on, right? Let's keep doing fib up through, I don't know, let's say 40. Right, I'll just start at 1. And we can watch it. It's going to slow down as we watch. It's going to get slower and slower and slower. So it's able to do the first ones relatively quick, right? The computer's pretty fast. I've got a decent computer here. But you can see it slowing down. Slowing down. Now we're at, 63 million or so? 102 million ones being added up. So there's that many different function calls that have to happen here. So this is actually a terrible Fibonacci sequence. So let me call this Fibonacci recursive, or Fibonacci bad recursion here, because that is bad recursion. Okay, that's the bad solution. A better solution here, and really this is, we can do it iteratively, Fibonacci iterative, in for nth term here. So this has nothing to do with recursion, but this is just the easy way to go about it here, is we need to track a couple things. So we have the current, and we have the previous, right? So we'll assume current is 1 and previous is 1, because that's going to make math easy here. And now we're going to say an int for current nth. Current nth is the nth term. And we're going to say while my current nth is, the current nth starts at 1. So while the current nth is less than the nth term, we need to keep on doing this thing. Right? So if it is 1, we're great. And when we're done with this, we'll return current. So if I ask for 1 is not less than 1, I'll just return 1. Great. Previous should be 0, that's right. So I guess maybe it's yeah, sure. So So if you ask for the second term, right, this loop should run one time. We're going to say my int next is equal to the current plus the previous, and then my current is equal to the previous. Current equals the next. Nope, sorry, I need to set them. So previous is equal to the current, right? And then the current is equal to the next. Nope, not that thing. Current equals next, right? So we're saying, okay, here's what the next one is going to be. The previous becomes the current becomes the next one. And then my current n plus plus, increase that by 1. So if I ask for the second term, I'm going to get 1 plus 0 is the next, which is 1. Previous now becomes 1, current becomes 1, current nth goes up by 1. And just for fun, let's print off both of these here to compare them, right? Because we know the first one was good, and then we'll call the Fibonacci iterative of the nth. So I'm going to take out the n line and just add a space here, just to separate them. So we'll make sure that the numbers match for the first 40 values. And you're going to see it's so much faster doing the iterative version. Notice it spits it out like immediately. There's no wait for that iterative version. And we're just making sure the values look like they match, but it's still very slow for that recursive solution. Right? And if you're not sure, right, we can take that one out, just comment it out, and you'll see it just spits it out like that for this iterative solution. It can count up 40 times super fast. Not a big deal to count up, right? Because it doesn't have to do those bazillion function calls, right? So that was the bad example of Fibonacci for recursion. Oh, wow. I think my control wheel got stuck. There we go. Okay, so you can do this better with recursion, right? So we can have a Fibonacci good recursion, but there's a trick here. This is the nth term. So what I'm going to do is I'm going to sort of cheat here. And cheat's not really the right word, but what I want to do is I want to have a public function that is very nice and easy and just has the nth term. And really, it's still kind of recursive here, so I can do the same check. So if we're at or less than 2, return a 1. I just know it. We're done. If not, what I want to do is I want to have a little private helper function. And again, we're not really doing anything private here in this function because we're not in a class where we can declare those sorts of things. But we'll just call this the Fibonacci good recursion helper. And this needs to take a couple things. So it needs the nth term, it needs the current nth, it needs the previous, and it needs the current. So this one needs more arguments. So the reason why we want this to be a helper function is I don't want someone to have to call Fibonacci and have to give me all these things, right? They call this good one here, and then I call the helper one. So if it's not 0 or 1, or term 1 or term 2, then I'm going to return my Fibonacci recursion helper. And I want to say the nth term is the nth term. The current term, well, it's not a 1 or a 2, so I'm going to say it's a 3. The current is 1, and the previous is 1. Okay? So this is the target term. This is the term I'm on. This is the previous. This is the current. Okay? So we're going to say here, we can check. So we can say my base case is if my nth term is equal to the current term. Current nth. I've reached the base. This is no more simpler than this. I know what the solution is. I'm going to return previous plus current. Done. So on the third term, I'm going to return 1 plus 1. If it's not that, I'm going to return a call to myself. Right? I'm going to call myself. Nth term is still the same. It's now current nth plus 1. Now the current term is the current plus the previous. And then the previous term is now the current. Right? I'm going to increase those values. Right? So the next nth here. So at 3, right, it's 1 plus 1. At 4, right, when I have to call, because it's not there yet, if I wanted the fourth term, I know what the third one is. I'm going to now increase. So now my new previous and current, those are backwards here. So I want previous to be current, and then the current becomes this one. Right, we need to make sure we match the right order. So this should be current, that should be previous. I don't think it's going to matter, actually, but it should be okay. So what happens here, right, if I want the fourth term, I'm going to say, okay, well, I asked for the third, current was third, it's not there yet, so it's now let's go. I want the fourth term. I currently have, now it'll be 4. My current is now the previous value, and the current value is now current plus previous. Right, so we can watch this one happen now. This is my Fibonacci good recursion. Let's do that one instead of the bad recursion. And again, we'll just check the numbers out here, see how well that works. And this is going to be super fast as well. Right? No waiting there. Now the problem is it's still actually slower than my iterative solution because every time I have a recursive call, I have to make new copies of these values in memory. So I have 4 integers now in memory for every call to this function, and every call is every nth. So it's, the iterative solution is still better than this recursive solution, but this is how, if we really wanted to use recursion, we'd kind of put it behind a helper function that is messy with all these arguments, and then we'd have a nice public function here that just takes the one argument, the nth term. So what we can do is we can give the good version, the easy to use version here, and then behind the scenes use the slightly more difficult one. Again, Fibonacci is not even a great example for it because the iterative solution is just better and it's not even all that hard. So what's happening here, we're using recursion in essence as a loop. It's just a loop here, right? We're replacing our while loop with that recursive call. We're saying keep doing this as long as they're not the same. Keep adding them together, right? It's the exact same thing we're doing here. We're just doing it with function calls instead of a loop. So that's, often if we're going to be replacing a recursive solution with an iterative solution, it's going to be some sort of loop, at least for these examples. Now, the Towers of Hanoi solution is much harder to do with iteration, with an iterative solution. And I'm not even going to bother showing it to you because it's just crazy. But the recursive solution is super pretty and super fast for the Towers of Hanoi solution. Let's flip back over the PowerPoint here, make sure we didn't miss anything. Countdown, stopping, yep, recursion, types of recursion. You can have this indirect recursion where A calls B and then B calls A, so it's like eventually recursive. Not too worried about that. Factorial is another good example there. This greatest common denominator is a really good example of recursion, and this is just super easy and fast to find your greatest common denominator of values. That ones are good. Recursive Fibonacci, sure. Base cases, yada yada yada. It looks like they assume 0. Sure, that's fine. Is the nth. Binary search is really fun. We'll come back to that one. I want to show you the Towers of Hanoi though. Here we go. So the idea with the Towers of Hanoi is you have 3 pegs and you have a series of disks going from larger to smaller and smaller and smaller. And the rule is you can't put a bigger disk on top of a smaller disk because it will crush it. So let's come back. Let's do like a new page down here. And let me zoom in a little bit. So let's imagine we had these 3 towers here. 1, 2, and 3. So we have a large disk, a slightly smaller disk, and then the small disk here. So I need to get all 3 of those disks from this peg over to this peg. But I can't move. You can only move 1 disk at a time, and you can't put a smaller disk on top of a bigger disk. So what I need to do is, well, I don't know how to move 3 disks, right? That's a complex problem. What I can do is I can move less disks. Well, even moving 2 disks is hard. So I know how to move 1 disk. Well, so moving 2 disks here, right? If I want to move the top 2, involves moving the top one here. So I move the small one there. And then I move the medium-sized one to the other peg. Boom. You got a medium-sized disk. And then I move the small disk back on top of it. Boom. Boom. Then I can move the third disk from here to here. Boom, there's the big disk. And then I can repeat the process of moving these 2 to the middle. So move the 2 to the middle involves moving the small one all the way over to here. I put the small one over here. And then I put the medium one over here. And then I put the small one back on top. So you can kind of see it's sort of this iterative solution where, well, it's hard to move more than 1. But to do it, you just move 1 less than that, move the biggest, and then repeat the process here. So hopefully you sort of feel that recursion. Kind of, it just, we're repeating this process. It's a complex solution with a base case. The base case is I can move 1. The harder case is I have to move n plus 1, or n disks. To approach the solution, we move n minus 1, n minus 1, n minus 1, and there's a really cool animation here. This is Tower of Hanoi visualization. Look at that, I Googled it before. So there's a really good tool out here. Where is it? think it's this one. Ooh, Liang has a good book too. Yeah, so here we go. So if we have, let's say, 5 disks, and we want to start. Right? Well, that's moving. We can't move 5, so let's move 4. Well, I can't move 4, let's move 3. Well, I can't move 3, let's move 2. I can't move 2, let's move 1. So I moved the 2 here. And now it's going to move the middle disk here to the middle, and then repeat the process of moving 2 back on top of it. And then we're going to move the 4th disk, once the 3 disks are moved, back to tower C, and we'll repeat the process. This animation is really cool. So now I've moved 3 successfully. Now to move the 4th, it's moving 3, moving the 4th, and moving the 3 back on top of that one. So I'll repeat the process. Move 2. There's a better one that you can speed up. Let's see. There's probably a better one. Liang's wasn't bad. There's a... Is it this one? Yeah, the speed factor here. Let's even 3D. Look at this. So let's move, let's just say 5 disks with 3. Usually we do 3 pegs here. Let's get the solution. And let's do a speed factor of 5, and we'll show it here. Yeah, that's much better. A little faster here. So we just keep repeating this process of moving 5 is the same as moving 4, moving the 5th, and moving the 4 again. 4 is the same as moving the 3, moving the 4th, moving the 3 again. 3 is the same as moving 2, moving the 3rd, moving the 2 back. Over and over and over and over. Right? This is recursive solution. Towers of Hanoi is really cool. So that's the Towers of Hanoi solution. The binary search is really cool, and it's a really popular way of searching. If we have some sorted data here, sorted list, sorted array, sorted vector of data here, and if we know it's sorted, we can do this. And we do this when we do the number guessing game, right? If I say guess a number between 1 and 100, you're going to guess the middle. You'll say 50. And I'll tell you too high, too low, or you got it. So what this lets us do is we cut out, so if 50 is too low, we know that 1 to 49 is gone, right? Can't be that. So now I have a new range of 50 to 100. I want to split the difference. I'll say 75. I'll tell you too high or too low. I'll say, oh, well, that's too high. So now 75 to 100 is gone, and I'm going to guess between 50 and 74. Actually, that should be 51, right? 51? 51, sure. And I'll split the difference. We're going to add them up, divide by 2. That's somewhere around 63 or so, right? And we'll say, oh, well, that was too low, so we'll cut those ones out, and now I have from 64 to 74 in my new range, right? And I'll search that one. So a binary search is guessing in the middle and cutting one half off or the other half off. So, and it turns out it's a really efficient way to sort things. So if I had tons of values in a list, if I just had like the Fibonacci numbers, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, on and on, 89, sure, and said, hey, do you have the number 3 in this list? Well, I'm going to count how many are in here, right? So I have indexes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So half of that would be 5, right? I'll guess at index 5, right? Is it at index 5? Is there a 3 there? No, that's too high. So I'm going to throw out the rest of these here, and now I only need to search from 0 to 4. So I'll split the difference. Okay, let's look at 2. Is it at 2? Well, 2 is too low, so split those out. I have 3 and 5. I'll guess one of them here. I'll pick, is it the 5? No, that's too low, so I have 1 left. Is it here? Yes, I found it. So what we got to do is we split the list in half and half and half and half and half and half again. So the most searches that you have to do is logarithmic, if you think back to your math class, right? Because the sort of logarithmic graph here where, you know, the bigger your n is, it sort of peters off as you go, which is really cool. So it's a very quick search if we have sorted information. So that's the binary search here. There's a quick sort algorithm, which is ways we can sort information. And again, it's a recursive way of sorting. You'll learn more about it in data structures, algorithms analysis, that sort of thing. But we can sort in that we're going to say, oh, hey, are we greater than or less than where I need to go? And we're going to swap them around. Again, you'll get into that in another solution there. So our recursive solution, right, our base case, oh, that's for that one here. If we can find a base case, that's the simplest solution. No more work is done. We know the solution. Great. There's one other fun thing we can do that we'll look at, which is a maze solver. So if we were to imagine we had a maze, let me put a new one in here, right? And we'll just represent our maze, right? This little 2D. You guys did a 2D maze navigator, right? Where we can navigate around a maze. Does that ring any bells? I hope that rings some bells here. We said, great. Okay, we either had walls, or we had, X's were walls, that sort of thing, right? We could go here, we could go around, maybe we have the end of the maze here, we have the start of a maze here, and maybe we got some walls here, like that. So what the base case is for a maze solver? Well, the base case is we're at the end. So my base is we're at the end. If we're not at the end, well, how can we approach the end? Well, we can either go north, we can go south, we can go east, or we can go west. If we didn't reach any of those, we didn't get to the end, right? Well, we're stuck. We can't solve the maze. So what we do is we say, okay, starting at the start position, we're going to try each of these directions. So starting at start, can I go north? No, I can't go north. Okay, can I go south? Yes, I go south. So now I'm here. So I'm going to recurse from here. Now the trick is, when you get here, if we say, can you go north? It's going to say yes. We need to make sure we don't step on ourselves. So when you're maze solving, you need to leave a breadcrumb trail. Right? So we'll leave a little breadcrumb and say, oh, I've been here, don't go there. So we'll say, no, you can't go north. Sure, go south. Now we're here. Right? So we have a call at, so we're solving at 0, 0, and then we're solving at 1, 0, right? And then we're solving at 2, 0, and at 2, 0, we say we can't go north, there's a breadcrumb, I can go south. Sure, so now we solve at 3, 0. Okay, now we're here. Can I go south? I can't go north, can I go south? Sure. So so each of these, right, we're at south. I need to mark the directions down. South, 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 south. Now at solve at 4, 0. I'm at 4, 0. Can I go north? No. Can I go south? No. Can I go east? No. Can I go west? No. Oops, that's no good. I need to mark it as a dead end. So I'm going to put a big D there, and then this call comes off the call stack. We've exhausted all of our options. We're back to solve at 3, 0, trying south. Well, now I'm going to try east. Now I'm going to try west. Can't do it, so that's a big dead end. Can't do that one. We'll erase that. And now we're back to solve at 2, 0. We've tried south. Now we can try east. Okay, so I'm going to go east. I'll go east. So now I'm solving at 2, 1, and we did south, so now we did east here. Okay? So now we go north, can't go south, we can go east. So now we're going to solve at 2, 2. 2, 2, right here. And now we're going to say, okay, this was east. I'm going to try going north. Sure, I can go north. Right, I can go north, I can go east, I can go east, I can go south, I can go south, north, east, or north, south, north, south, north, south. Eventually I'll get there, right, where I keep having this call on my call stack here. So 2, 2, and then solve at 1, 2, solve at 0, 2, solve at 0, 3, solve at 0, 4, 0, 4, 0, 4, right? And then we're working our way down. So it's 0, 4, 1, 4, 2, 4, 3, 4, 4, 4, reach the end. So we don't always find the most fastest, easiest solution here, right? Going up and around took more spaces, but we're going to find a solution. Now imagine there was a wall here, right? We do dead end, we try south, we try north, can't go south, we tried south, can't go north, we try south, we'll try east. So you can find more than one solution. This is a recursive backtracking solution. The idea is if we reach a dead end, we just backtrack and go back to where we were before. Right? So recursive backtracking solution is a good example of using recursion, but you can imagine that exhausting all of these possibilities can get a little crazy. Right? If we have a giant maze, if we've got like 1,000 by 1,000 maze, we've got 1,000 by 1,000, depending on how many different directions we go. That's a lot of recursive calls, and we might eventually run into trouble here. Well, I did want to show you with countdown what happens here. For fun, let's do countdown of like -1. And notice we don't handle a negative option in here, so maybe less than or equal to 0 is better, because what we're going to get is bad stuff. It's counting down, counting down, counting down. Let me pause that here. Let me just comment that out for a minute. I want to show you what happens here. So we'll see in the call stack as it's running. Boom, we get the stack overflow, right? And you can kind of see over in the call stack, we got to negative 4,793 before we exhausted our call stack. So you can have quite a lot of calls in the call stack here, but eventually you'll exhaust it. So like 1,000 by 1,000 maze, if we have to try all these different paths and every path is another function call, we can run into trouble. So they do have limitations, but it's a nice simple way of trying to solve your problem there. All right, so that's recursion. I'll get you another video here for our final project, and we'll go from there. Guys, reach out if you have questions. I miss seeing everyone, or at least chatting with you on Twitch. Hopefully we'll be back the week after Thanksgiving, and we can get back to somewhat normal, 2020 normal. You guys take care.